in earlier last class we discussed field theory of a scalar particle, scalar, I just said scalar, well it will become clearer later as we go along. So, it was a one field which was a real field and we quantized that. Okay, now, we let us continue the story in the same lines, but we will bring in more, but remember that was a boson. The number of particles for a given wave number or given state could be 0, 1, 2, 3 like that. Okay. Now, we will also introduce fermion in today's lecture. So, this is called many body physics. I am not doing relativistic right now, I am kind of skirting it out because it has pretty tedious algebra. Okay. So, we will do that later. So, let us start with Schrodinger equation, again start with classical Schrodinger equation. So, this is the Lagrangian which we derived, or well we started from this and derived like Green's function and so on. So, from this Lagrangian we can derive equation of motion, no, that is straightforward, Euler-Lagrange equation. For time being we say we will discussing free particles. So, we set V equal to 0. Okay. So, this potential is 0. So, this is basically free particle, no, this is potential, this is coming from momentum squared P squared by 2m, P squared operator. So, I am setting Vx equal to 0. So, it is a basically free particle. So, in your standard particle course this is called free particle Schrodinger equation, single particle. Now, we will quantize it, that is the idea today, we are going to quantize it and we will get many particles. Okay. So, Hamiltonian for this system is this, which can derive, and I derived it in the class. From this Lagrangian I can derive Hamiltonian, and total this is Hamiltonian density, this is Hamiltonian density. So, this is total Hamiltonian over whole space, and Green's function is this. Okay. So, Green's function we can derive from this equation. For me I kind of derive Green's function from the equation is straightforward from here. Okay. For potential 0, this potential 0, we will introduce potential later. In fact, today's class also we will see one potential will be introduced, we will do it as a perturbation. Okay. So, a free particle. So, I am going to now start going to Fourier space and starting to quantize. Okay, that is what we will do. So, this is Hamiltonian. So, now this is only field phi. It turns out for this we can write down momentum density, but we do not need it. So, some of it is like art, how to do quantization. So, for the earlier lecture for oscillating field we had both momentum and phi. So, we quantized both pi and phi and there is a commutation relation for them. Okay. Today's class will be a bit different. So, we have phi x. So, this phi x becomes an operator. So, it is written in terms of phi hat k, it is a Fourier amplitude, but this is an operator, this is not a number, it is not a real number or complex number, it is a operator. We can invert it, phi hat k is phi hat, it is just invert. Okay. So, this we defined it, but I do not need pi and I can substitute it there. Okay. So, the grad will give us k squared, grad square will give us k squared, okay, and this phi squared will become phi dagger k phi k. Okay. So, this is Hamiltonian. So, you see that we have become basically pretty similar structure, but I do not have momentum pi dagger pi. So, in some sense I already quantized it, no, I mean, so my Hamiltonian, this is an operator and I have this written as a product of phi dagger phi and for wave number k, and okay, do not interpret this as a oscillator now. Okay. Earlier we interpreted them as oscillators, but this is sum of smaller, well, some of Hamiltonians which are basically phi k dagger phi k, and there is 1 by 2m. Okay. Now, dagger, so interpretation of phi dagger is same as before, its transpose conjugate, and so this sum I write as integral. Okay, sum is so we are doing with infinite box, so the sum is basically integral. Okay, so commutation relation. So this is what I was mentioning. I started discussing this in the last class. So in quantum mechanics, there are of course lots of particles, but two electrons are indistinguishable. In classical physics, we have stones, right? I mean, two stones or two balls. It could be identical looking balls, red ball, but they may look identical, but we can distinguish it from the trajectory. Okay, so there is a trajectory of particles, and we know the trajectory is well defined. Okay, trajectory is well defined. So from the trajectory, I can distinguish the particles. So classically, the particles are well defined. Okay, and they are distinguishable. So that has a consequence. I mean, the distribution in statistical physics, this is called Boltzmann distribution, no, for classical particles. Okay, but in quantum mechanics, these particles are indistinguishable. Okay, so the experiment which you can think of scatterer. Okay, and I shoot two electrons from far, 1 and 2, but you see electrons are quantum particles. So I can't track it. This position and momentum of these particles are not well defined. In fact, I do the experiment, I shoot something and then I observe it sometime later. So this particle will come out, okay, come out here. So this particle A and particle B. So there is no way you can figure out from this is a postulate of quantum mechanics. In fact, experiments also do not tell you whether particle A is 1 or 2. Okay, here I am not destroying the particle. There is no creation destruction. This is just pure quantum mechanics of particles. Okay, so this particle A and particle, because in between I cannot track it how the trajectory went. Like, is it went like that or did it go like this? So there is a, in fact there is no trajectory. So in fact there was a wave function which was here and then it came out, and when I measured it I got A and B. So this is called indistinguishability. So photons, two photons are indistinguishable, quantum particles are indistinguishable. That is one major postulate which happens to be true in all experiments. It is a consequence. So fermions obey statistics which is different than Boltzmann statistics. So classical particles obey different statistics in statistical physics and quantum particles differently. So bosons, Bose-Einstein statistics, and fermions, Fermi-Dirac statistics. Okay, I will not derive it in this course, but they are different. Okay, so now let us see how to use it in field theory. In fact, field theory makes it very clear. Okay, that is beauty of this formalism. So think of you have two particles, you create particle 1 and then particle 2. So I create A dagger 1, then A dagger 2. Dagger is a creation operator, no. So we have two particles. Okay, it happened in by the field theory. So let me just make, in field theory you can create particles and destroy particles. So just imagine that in some experiments in nature these two particles were created. It's, or you can do so you can create two particles in a different way. You can create particle 2 first and particle 1 later. These are operators. End result is the same, right. So you can't distinguish which was done before, which was done later. These two particles what we see in experiment we will just see two particles. So this this product of the operators is identical in terms of observation. Okay, it turns out you can, so this one can change by a phase, in fact by a number +1 or -1. So this could be 1 or -1, this product, the difference can be 1 or -1. It turns out it can also have some e to the power I phi kind of stuff, which is also a new set of particles, but we will focus only on 1 and -1. If it is 1, then that is a boson, right. We discussed that in the last class. A dagger commutes, A dagger K1, A dagger K2 commutes, right. But if it is -1, then they are not commuting, right. So if I multiply two operator A B, I get minus B A. So, this is called that does not commute, but this is called NT commute, NT commute. Okay. So, commutation from standard quantum mechanics, we write A B, two operators A and B, we write as A B minus B A, right. If they commute, then this A B commutator A B is 0. If it does not commute, then I get some finite number, or it could be also an operator. Okay. But if NT commute, then we have different symbol. We write as a curly braces A B, which is written as A B plus B A. So, if A and B NT commute, these are operators. Okay. If A B NT commute, then this will be 0. Okay. So, fermions NT commute. Okay, fermion operators NT commute. Okay, this is new. I believe if you are not done field theory, then this is the new thing which you learn in field theory. So, this is what I stated it here. So, A dagger, we create two particles with momentum P1 and P2. We can change the order, but it turns out this product A dagger P2 then A dagger P1 is equal to A dagger P2 A dagger P1 with factor lambda in front, and lambda can take value +1 and -1, and 1 is boson and -1 is fermion. Okay. So, this is how we construct the full fermionic field theory and bosonic field theory. Okay. So, boson we already studied that. Okay. So, but now let us just revise it, it does not hurt. Let me make one more remark. Some people use this commutation AB commute as plus and NT commute as AB minus. Okay. So, this is another way to write it, but I will follow braces. Okay. We will not follow this notation. So, boson we saw that A dagger K prime commute, no, the creation operators commute, destruction operators also commute, but creation and destruction operator together they do not commute. So, AK dagger is 2 pi cube delta K minus K prime. Okay. So, that we studied, we derived it in fact. Well, either you have to use a real space commutation as a postulate or Fourier space commutation as a postulate. This is a postulate, like this Heisenberg uncentered relation generalized to fields. So, you can ask why this is how nature is. Okay. So, we said that well in field theory we have a state psi, and a state psi is specified by number of particles in each state, each substates. So, this is corresponds to wave number k1, k2, wave number k, like that. Okay. So, this I defined it earlier. So, we have various states of the system, and you see how many particles are there in different states. For bosons we can have more than one particle or 0 particles, and it has a very important consequence. Okay. You will see it very soon. So, this is state psi, and we have two operators, very important operators, creation operator and destruction operator. So, destruction operator with k is the state, you can call it k is the state or wave number, okay, k state. So, AK acting on psi will work on this number of particles Nk, it will just destroy one particle. So, this is kth substate, okay, and then there are 3 particles, so will just destroy one and bring it to 2. So, Nk minus 1 is the prefactor square root Nk. So, this property of creation operator, a destruction operator. Now, creation operator Ek dagger, if you act on this psi, this state, then it will increase the number of particle in that state is Nk plus 1, and the prefactor is square root Nk plus 1. Okay. So, if I act Ak dagger on this one on the full state, but this k will tell you which state to which substate to act on. I hope this part is clear. So, in Fourier space we have many wave numbers. So, like the photons in this room. So, I look at particular wave number and I want to create or destroy photons in that wave number. Okay. So, or hydrogen atom we have many levels, no. So, for a given state whether we can create an electron or destroy electron in that state, in that LM cells. Okay, so that is what it means. And then we have number operator AK dagger AK, which is acting on psi will give you NK for that given state K, and Hamiltonian is AK dagger AK plus half omega K. Okay. For Schrodinger equation, omega K is defined, we know that is h bar squared K squared by 2m. Okay. So, for Schrodinger equation we will use K as a state label or substate label, if we call it. Okay. If we call this is a state, then these are substates, no? I mean they are levels of the state. Okay. So, this I did it in the last class. So, we are doing it bit fast, and in real space their corresponding commutation relations are these. Okay. Right now for Schrodinger equation we do not have pi. So, we will have only this, and well we can construct pi, but let us ignore this part. Okay. We will just deal with, for Schrodinger we will just deal with AK dagger AK, okay, with Fourier number as a state label. Now, fermions, okay, this is something very important, and we will see how the properties of fermions come out in field theory. Okay. So, again state psi is same as what we described, N1 N2 Nk, but we will soon realize because of anti-commutation relation that N1 or N2 or all this can be values 0 or 1, it cannot be 2 just because of anti-commutation property. Okay. So, as I said, AK dagger AK is 0, anti-commutator, not commutator, and same with creation operators. But AK dagger and AK, this one AK dagger is not 0, it is in fact delta function. Okay. For okay, all right. So, particle numbers I am going to derive it in the next slide, it is either 0 and 1. So, you will just see the derivation in the next slide. In the real space you replace this commutator by anti-commutator. Okay. This square brackets are replaced by this relation. So, I will give some homework, you just work out using this property, you can basically can get some simplify operator. So, we will see one example here. Okay. Let us see. So, I will focus, I will basically drop symbol k. Okay, I am dropping symbol k. So, I am focusing on one state. Okay. So, I am just do not want to carry this k, but just imagine that we are given a given wave number a k, and so anti-commutation is 1. So, I h bar, so h bar is there, no, not I h bar, h bar is there and delta function. So, since the same wave number, delta has become 1. So, okay, you can think of instead of infinite box, you can think of a finite box with the canonical delta. Okay. So, from this, so this is clear, no, this is anti-commutator. So, I have to add, not subtract. So, I get a plus 1. Okay, A dagger plus A dagger A. Now, what, so I just rewrote that is A dagger equal to 1 minus A dagger A. So, I just take this to here. Now, A dagger A is what? Is a number operator for that given state. Okay. So, A dagger is 1 minus n number operator. Okay. Now, we know that A is 0, right. So, this anti-commute. So, A anti-commute is 0. So, A plus A is 0. So, that means A is 0, right. So, this is 0 and this is also 0, but the product of two operators is not 0. A dagger, sorry, creation and destruction operator you multiply, then is not 0. Now, so I am just going to look at this operator n into 1 minus n hat. Okay, look at this. So, what will that be? N number operator is A dagger A, this one. What is 1 minus n operator? This 1 minus n operator, which is 1 minus sorry, this is A dagger, right. 1 minus n is I just derived it. So, you got this. Now, you can see that in between there is a A sitting there. So, A will give you 0. So, you just apply any vector psi. So, psi will act on A dagger, so that will give you phi, but A acting on phi will give you 0, because A is 0 right from here. So, this is 0. Okay. So, what does it mean? So, if I act this on any state psi, eigenstate psi, then I will get either n to be 0, if psi is the eigenstate of this operator, then n will be 0 or n will be 1. Okay. So, this implies that n is either 0 or 1. Okay. So, this is coming from the property of empty commutation of these operators. Okay. So, either the state is empty or there is only one particle in that state. Okay. It just follows from this this operator. This is pretty strange thing, but it just follows. So, this Pauli's exclusion principle for fermions. So, these are called fermions. These particles which obey this anti-commutation relation are called fermions. These are different than bosons. Bosons can have any number of particles in a given state, but this can't 0 or 1. Now, you can easily see that A acting on, so this is a vacuum state. Okay. So, in a vacuum state there are 0 particle, I cannot destroy, well if I just act a destruction operator then I will get 0, but A acting on 1 will give you 0. So, there 1 particle, I destroy 1, I will get 0. What about A dagger acting on 1? 2, but 2 is not possible. So, this is 0. Okay. So, A dagger 1 is 0. So, it just gives you, it is the empty state. So, A dagger 1 is 0, A dagger 0, A dagger acting on the empty state, if you can create and you can get 1. Okay. So, yeah, you have to be careful, this is different than bosons, but if you bring in spin no problem, you have to count the down spin up spin separately. No, the n will not become different. So, n up operator 1 minus n operator is 0. So, as a given state, so you have a given wave number and spin, if you like you can add it, or and also same with n down. Okay. So, this is Pauli's exclusion. In hydrogen atom we know I can have in one state 1 up and 1 down, but you can't have 2 up. So, so this is where we will take a break, and if any question you can ask me. Any questions on this? Yeah, there is only 0 and 1. Number of particles is 0 or 1. No, wait. So, in a system there will be many states, and each state there can be either 0 particle or 1 particle. Okay. So, in hydrogen atom we have many states, no. So, in each state we can have only 1 or 0 spin up particle and 1 or 0 spin down particle. So, remember that there are states I just put straight horizontal lines, and you can fill according to the rules of bosons or fermions. Alright. So, we will see one example, free fermion, free Fermi liquid, that is what we will do. Well, simplified free Fermi liquid. Any other question?